Hello and welcome to another video. This is the first in a series of videos aimed at introducing beginners to Bifrost Fluids in Maya. In this video I'll be focusing on the absolute basics of creating a Bifrost fluid simulation. We'll cover things like creating the emission, adding colliders, understanding how the simulation actually works, and configuring Maya and Bifrost itself to help with some of the scene optimization, performance and playback. Just as I've done with my previous Bifrost videos, I'm aiming these tutorials at any users who are maybe more artistic than technical, or if maybe you've tried to create some Bifrost fluids in the past and have just struggled to get anything out of it. And just as before with my other Bifrost videos, I'm not going to make any assumptions on your knowledge, unlike some other videos where maybe they show you a good tutorial and show you how to set things up, but they maybe skip over some of the fundamentals and details, and you can get lost and frustrated when you're trying to basically do your own thing. Now, this is a long video and it's longer than some other Bifrost tutorials that you've probably seen, but I wanted to cover as many of the basic Bifrost fluid principles in one video before then moving on to something more advanced. I've broken the video into different chapters so you can skip parts or go back and watch parts again, and that way you can follow at your own pace. Now, before we start trying to do our first simulations in Bifrost, we need to just check on Maya and have it set up in a particular way, which will not only help Maya and Bifrost work better for you, but will also give you a better visual feedback in the viewport. The options to look at are in the preferences. The first one being is the cached playback. Now, cached playback has been around in Maya for a while now, and each time they tend to update it to support additional features. Now, what it does is it basically allows you to see changes made to your animation without the need to do a full play blast. And because previously Maya wouldn't always be able to draw the scene quick enough in order to reflect the changes, so you often had to do a play blast. With the caching, what it does, it caches frames in the background so that it allows Maya to hopefully maintain a real-time speed in the viewport. So there's a few options here to look at, but it's usually on by default, so keep it on for when working with Bifrost. You can allocate a percentage of your RAM to this, but whatever you put in here, you're not going to be stripping Maya of its RAM allocation overall. And I'll cover some of the other features here whilst we're actually working away. The next area to look at is the animation playback speed itself. Now, my frame rate for my scene is going to be 24 frames a second because that's what I want to work in. And currently my playback speed is set to 24 frames a second. It's real time. So that means that Maya will try its utmost in conjunction with all the caching to maintain a 24 frames a second real time playback. Now, what it will also do, it can sometimes skip certain frames in order to maintain the frame rate. And sometimes you don't always notice this. That might be fine. However, when you're working with simulation data and data that requires a heavy CPU allocation, then you're going to start to get some jerkiness appearing, and that's not really going to work very well when you're trying to do simulations. So what you're better off doing is setting it to play every frame. Now, what play every frame does is it means that all frames in the animation or in your scene will play, and they'll update each other before then displaying the next frame. And this works a lot better with simulations because simulations are also calculated on a frame by frame basis. You can change the increment here as well. So you may want to play back to say to 2, which basically means it will only play every other frame, but I want it at 1, which basically means it's playing each frame sequentially in order. The other thing to do as well is to clamp the playback speed itself. So you can set this to 3, which basically means there's no specified frame rate back and it will try its best to do whatever and it will scale accordingly. However, you're not going to get a very accurate representation in the viewport. So what you're better off doing is actually setting it to 24 frames a second here. And that means that this clamps the playback speed to this particular value. And this is really useful when you're working with scenes that have fluctuating levels of CPU activity. So particles, cloth, fur, hair, and Bifrost simulations are very much those types of scenes. The next options you want to look at are the Bifrost options themselves. They can be found under the Bifrost Fluids menu at the bottom here, Bifrost options. The thing you want to have on straight away is enable scratch caching. And this is really, really useful. So the scratch cache is like a temp cache to help speed up the playback and scrubbing as well. So it's separate to the cache playback in the viewport, because this is caching animation data, whereas this is actually caching simulation data. And this allows quicker previews of low to medium resolutions on your simulations. It's not the same as caching everything out as your final output. And what it does is it stores the simulated frames in memory, but then it offloads them to a temporary file on disk. And it's automatically flushed and regenerated whenever you change the simulation. If you change any value at all, it will automatically flush and then regenerate a new cache. It will also be flushed and deleted whenever you close the scene and start a new scene. Now I've got it turned on here. You can allocate RAM usage to this as well. And I've given this a value of 16 gig, which is a quarter of what I've got in my machine. Of course, you can set it accordingly based on whatever hardware you're going to be working on. You can also override the disk location as well, because by default, it actually stores it on your C drive if you're using Windows. Now, my C drive, I want to keep completely free of this. It's not going to chew up loads of disk space, but I don't want it on my C drive. But I actually have a D drive attached, which is a solid state drive as well. So I've decided to cache my data to that location instead. So I would also do that if you're able to, but only if you've got a solid state drive. I wouldn't do it if you had any other type of hard drive inside your machine, or if you've got a network attached drive that you're going to be using over Ethernet, for example. Those types of locations don't really work for this type of cache data. There's another option here as well about enable background processing. What this does is sends any requested frames to the Bifrost computation server in the background. And this can sometimes allow you to use Maya interactively whilst your frames are being computed and cached in the background. Now, I've had mixed results with this, so I don't always have it on by default. And also, if you have it turned on, you don't have the ability to disable the scratch cache. So for the time being, I'm going to leave it alone and have it deactivated and just go with my scratch cache. Those are really the only options you need to look at for now. I'll go back to some of these whilst we're actually working to give you an idea of what happens when you change certain parameters. Now we're ready to start creating our Bifrost simulation. I want to cover some of the basics and some of the fundamentals that you're going to need to know before then going on to anything elaborate. And the areas I'm going to cover are really quite important because it's very easy to go wrong even in the early steps. And go wrong here, and then it can greatly affect your workflow and also the final result. So when starting, many people will go to the Bifrost menu, and with nothing in their scene, the scene's completely empty, they'll go to create liquid. The Bifrost objects are added to our scene. Our timeline seems to have cached correctly. So many will expect to see liquid of some kind, but when they press play, we don't get anything. Now, the reason for that is that there's no emitter object in the scene. And Bifrost needs an object of some kind to be defined as the emitter. And the emitter is basically where you want your liquid to actually start in your scene. So that it can start in then emitting particles, which will then become voxels, and which will then become your liquid. So it's a good idea to have an idea of what it is you want to do before you then start to create the fluids in the first place. So even at this stage, people can expect to see something and they get a little bit frustrated. But it's very simple to add an emitter, even after these nodes have been created in their, I guess, empty states, if you want to call it that. And you can just about add anything to the simulation after it's been created. And they appear here in the add menu. So you can see that obviously it's broken down to simple sections. So you create here and then you add things here. So I'm going to create a simple object, a sphere. I'll just make the radius 20 and then I'm just going to move it to somewhere in my scene like here, put it a little bit above the ground, and this is going to be where I want my fluids to start for whatever reason. To now add them to our simulation, we select this node here, Bifrost Liquid, shift select the sphere, go to the Bifrost Fluids menu, and from the add section choose emitter. Now you should see what looks to be like some blue bits or points around your object. These are your particles. But if you don't see anything, check which frame you're on in the timeline. Now the particles will be emitted from frame 1. but we're at frame 79. So therefore, that's why we're not seeing anything and why nothing's appearing in our HUD. So if we quickly return to frame 1, then your particles will appear. And we can see now, if we just zoom in just a little bit, we can see that we are emitting 362,000 particles, or just over. Now, the size of your emitter object will then also have a bearing on how many particles that will be emitted. So you need to bear that in mind as well. And I'll talk about scaling in a little while. Now, if we'd had an object in our scene already that we wanted to be our emitter, then we could have selected that first and then gone to the Bifrost menu, chosen Create Liquid, and Bifrost would have then created particles straight away. So either method can work, and it's entirely up to you what you prefer. Also, if you wanted to add additional emitters to this single simulation right now, you can do that. Just use the method I just did when I added this emitter, and you can add as many emitters as you want. Now, at this point, you can hide the emitter. You might not want the object in your scene, so you can hide it very simply, but don't delete it. Deleting it will essentially break the connection to Bifrost and therefore break your entire simulation. So we have our particles. Our timeline has cached out completely from 1 all the way to 120 frames. So many will now expect to see some liquid, but when we play back, what we see is like a spherical blob that kind of is shaped like our emitter, and it just falls away from our emitter. Well, this blob, if you want to call it that, is our liquid. What's been created here is a static mass of liquid. And I'm using the term liquid and not necessarily saying it's water or any other kind of substance. I'm just calling it liquid because that's all we've got right now. We don't have anything specific. And the reason why it's falling away is because of gravity. And this is a really important key concept to remember now, is that as soon as you create these Bifrost nodes, real world physical values and properties are applied. So your liquid will behave as it would do in the real world, and water doesn't hover or float in midair. You know, it will have gravity on it like anything else, and therefore that's what's affecting the liquid, and therefore that's why it's falling down into the ground, or essentially it will fall off into infinity, or however long your timeline goes on for. When we see our particles fall like this, you'll notice that it starts off blue and then it changes color. Now these are particles represented by points, and essentially this is a color channel that's been added to those points in order to represent certain values. And these all make up what are the display properties for the actual points themselves. And we can change these to make them easier to see, no matter how many we've got actually being emitted. So if we go to our Bifrost liquid node here, bring up our attribute editor, and there's a number of tabs all open here. They're the same names as what we've got here individually in the outliner. Now I'm going to look at the liquid shape tab here, and this is where we basically set the display properties for your simulation. So first are the basics at the very top, and we've got 3 options: bounding box, particles, or voxel. So the bounding box is this cube here, which is surrounding our simulation. It will follow the simulation wherever it goes, or however big or small it gets. It will scale up accordingly. Of course, you can turn it off if you don't need it. Next up, we're displaying as particles, but you can choose to display as voxels. Now, there's nothing wrong with that, but voxels can give you a better visual quality. But even this choice at this basic stage can affect performance. So if we look now at our playback range, because it would have cached very quickly, because the simulation has been computed already, we're just changing the actual display properties. If I press play now, the playback is significantly slower. So even though it takes a while to get going, eventually speeds up, it's still slower than what it would be if we changed it to particles. So the difference is quite significant. So it's really better to just display as particles. Some people do display as voxels, maybe if they want to do play blasts or any kind of renders. But I think for when you're working with the sim in order to get it working, particles are best. Now we can change how the particles are represented in our scene, and we have 2 basic choices. We can have points or spheres. And again, as before, each choice can have an impact. So with points as it's set right now, we can change the size of them so they become more visible. I'm going to do this with this point size value here. So if I drag it, you'll see the points get larger. So I can set this to say to 2. We can also control the maximum amount that gets displayed in our scene, no matter how complex the simulation becomes. So at the moment, we're emitting over 360,000. I could drag this down to make sure, say, it doesn't go above 400,000 or whatever I want to. So I'm just going to set that there and leave it as is. Now, if we choose spheres, for example, that will give you actual shapes on the simulation. And again, we can control the size of these with the sphere radius value here. But again, these will have an overhead on the performance. If we play back the sim now, again, it's significantly slower than it would be instead of being displayed as points. So again, if we go back to there and change the points and press play, you see there's a big difference. I'm trying to keep the playback as real time and keep the frame rate here in the bottom corner of my viewport, so you can see the performance of my machine. The next attribute to look at is the color channel. At the moment, we are displaying velocity, and that's the default value that gets applied with this gradient map as well, which you can collapse via this color channel remap. Now, in very simple terms, we're displaying velocity here as part of our simulation. So it basically means that the blue areas, or the points particles that are displayed as blue, have little or no velocity. And then and that's what they start off with as blue. Then over time, as we scrub the timeline and they gather more speed and velocity, then they gradually turn to white. So these values can be really useful when trying to analyze the behavior of your simulation. And of course, you can set this to all these types of values like density and UVs and stickiness bandwidth if you start to get particular types of liquid that you're trying to create. So we're just going to keep it at velocity for now. Now, there's a lot more values here to go through, but I've only covered the absolute basics for now, because that's really all you need to know. You can, of course, on the color, if you don't want colors altogether, just uncheck this box here, and you'll just get standard light green selection color that Maya displays. But most people who tend to work in this tend to have some kind of color remap turned on. So we've covered the basics for the display, and we can choose to maybe look at some others later on in the video. Now, these values are okay, but they're only changing the display of the particles and the simulation. Even if we've made some changes here to maybe enhance the performance, you still might not be getting a reasonable playback speed. Our one's not too bad, but then again, I've got a reasonable hardware spec. But again, I'm still emitting quite a few number of particles. And they more or less stay the same constantly throughout the length of the entire sim. What we need to do now is to improve the simulation and also get any performance back, is actually go into the properties of the liquid simulation itself. And this is done by selecting the Bifrost liquid properties here. You can select it individually here from the outliner, or just go to the extra tab here, also in the attribute editor. This is where you'll be spending a lot of your time when working with Bifrost liquids, because this is where you can really change the type of simulation and also the behavior of the simulation as well. But there's one property here that is most likely the single most important value above everything else. And that's this one here under the resolution. It's the master voxel size. Now, there are other values that are also important, but the voxel size trumps them all in my humble opinion, because it's the main control for the resolution of your Bifrost simulation. Now, without getting too deep into voxels right now, because it can be quite complex, and I want to keep this video as simple as possible, there's a very simple principle to apply here with this value. So by default, Bifrost creates the nodes here and applies a value of 0.5 units in the master voxel size. So increasing this number above 0.5 will reduce the number of particles and voxels, thus resulting in a better performance, but your sim will have a reduced quality and accuracy. So let's try that now. So with 0.5, I'm going to say, let's take it to 0.7. So when I do this, Well, notice there was a change there, and we're now only emitting 174,000 particles and then just over 230,000 voxels. And straight away, our simulation has started to cache because we've made a change to it and it needs to recompute. And we can see it starts to even speed up here. Even the scrubbing is that bit quicker. So this is where you can really start to make some improvements to get your performance back. And of course, it's still pretty high. 174,000 is still pretty high. So we can increase this number. Now, in terms of the other direction, if you lower the value below that 0.5 default, this will increase the number of particles in the simulation, giving you greater quality and accuracy, but the simulation then requires more computing time, which then will affect performance. So it's often a good working practice here to increase the master voxel size to a value whereby you can do tests and any kind of previews, and then gradually lower the value over time to get the quality that you're happy with for your final result. So again, we can continue to actually increase this. So to say 0.9. And again, slight delay. We're now just over 100,000 particles. And again, if we could even sort of really go nuts on this and go 1.5, and we've now gone too high and we've pretty much blitzed our particles altogether. So again, you've just got to get the right value. The trick is just to increase the number just enough to get enough performance, but not so much like I've done here, where I can't see my simulation. So I'm going to have to lower the value back down in order to get some points displayed and therefore some kind of simulation to actually work. So I've set my master voxel size now to 1, which is quite high, and I'm literally only emitting just over 79,500 particles, and you can see the voxel count here as well. And we've got a really good playback rate. So that's fine. And you might be thinking, well, I'm clamping, remember, at 24 frames a second. So of course it seems to be performing pretty well. So if it maxes out here, the temptation can be to go back into the preferences and change this so it's completely free, or even go back to 24 frames a second real time and then go, well, look, okay, look, it's playing back in real time. I don't need to play every frame. However, you've got to be very careful here not to get sucked into this, because this is only a single emission emitting just under 80,000 particles, and it remains more or less fairly constant all the way throughout. We've not got any other things going on in our scene. There's no collisions or any other simulations, and this number will likely increase. So you've got to be very careful not to be lured into the idea of changing a few things now, thinking that you've got a really fast performance when you've barely only just started. Now, we just have one emitter creating particles and our liquid, but this might not be what you want. So how do you change this? So Bifrost has no presets or templates that represent different types of liquids that you can just simply call upon and then load and then apply them to your simulation. To create a particular type of liquid and effect and behavior, you have to adjust all the properties that are contained here, all in these tabs. Now, you might not want the static mass of liquid like what we've got now, and instead you want to have liquid to be flowing, say as if it's from a tap. Now, to do this, you don't need to create a whole new emitter. You can actually change the properties on the emitter object itself. You can go to the properties of the current emitter by selecting the emitter properties here from the outliner, or looking at the same tab inside the attribute editor. Then look for this property just here under properties, continuous emission. The box will be unchecked. You can then check it. What this will do now is that the simulation will now start caching again, but after a few frames, when we start to scrub, we should now see our liquid starting to flow continuously as if it's been turned on from a tap. And as before, gravity is still applied, so the liquid will continue to flow into infinity, or however long your timeline actually is. But the key thing is now is look at the number of particles. On frame 1, we had just over 79,500, which looks okay. But because the emission is now continuous, this number is going to increase with each frame of your timeline going forwards until we get to the very, very end. So if we scrub now, because we're just about coming to the end of the caching, even if we press play, we've got good feedback, good performance. But now, when I stop it about here, we're now up to 427,000 particles. So now we might have to go back to the master voxel size because we were fine at this point in time, but we've changed the type of emission. So now when we get further down here, we've got quite a few particles now in our scene, and of course that's also going to affect the computation time and performance. But if we just played this back now, it's not actually that too bad. We get a weird delay at the very start, so it takes a while to get going, and then once it does, the velocity picks up, and then we've got what looks to be like flowing liquid. Now I'm going to go back to the master voxel size and actually try increasing this a little bit more to see if we can improve the performance, taking into consideration where we might be further on in the timeline. So I'm just going to set to say 1.2. So now we've gone down to 52,000. Let's see if I can push this just a little bit higher to 1.5. And we've just kind of blitzed it then. Oh, there we go. So it just needed a bit of a refresh. So we're getting some particles. So on frame 2 at 31,000. So again, we're getting there. So we just need to give it time to cache, and we'll get all our particles displayed. So if we scrub the timeline now, we can see even when we get towards the end of the timeline, we're still just under 200,000 particles here. When we get to the very, very end, we've only got to 224. So we've reduced the quality enough to get a good amount of performance, and we've maintained a reasonable looking simulation. Now the liquids will keep flowing now until we change something. They'll just keep falling into infinity. So we need to do something that will stop these particles and this liquid flowing, just as we would have to do in the real world. So as a crude and very simple example, I'm going to create a ground plane, which I'm just going to scale up to say the limit of my grid, like I've got there. What I want to do is that this will be now my collider. So I want my liquid particles to hit this and not stop, but it will stop them going off into infinity. So just like we did with the emitter, we select the Bifrost liquid, select the actual ground object, go to the Bifrost Fluids menu, and then we want to choose under the add section collider. This tells Bifrost now to treat the ground as a collider for the liquid simulation. So whilst we're caching the liquid now, we can begin to scrub. And what will happen once we get up to that point in time is that our liquid will hit the ground and hopefully spread like a splash, like any liquid would when hitting something like a hard surface. So let's just scrub a bit more. We're not quite there. If I press play, I can try and play and scrub at the same time. There we go. So we're getting a kind of effect that we would usually expect the behavior of liquid to be when hitting a solid hard surface. And of course, now we've added that collision object, it will take longer to compute and cache, but we're still getting a pretty good performance and playback. But of course, the more things you add, making the sim more complex, the computation time will get longer. And of course, you know, even if you set the voxel size to be really high, it will still take longer to compute each time, the more complexity that you actually have. Now, if we go to a frame where the liquids are hitting our ground like so, we take a little bit of a closer look here. Now, if we just look just about there, there looks to be almost like a gap between where the particles are supposed to be hitting the ground and the simulation itself. We can see this better from a side view. Now, that's not really 100% accurate, and this is what can happen when you increase the master voxel size. There's less particles being emitted, and therefore there's less particles being computed, and we get this discrepancy. Also, what can happen as well is that there's not enough information, or shall we say detail, in the collision object for Bifrost to create an accurate collision. You know, this is just really a very flat plane. It's not really a very solid object. And really, when working with Bifrost and collision objects, it's better for the collider object to have a thickness of some kind, even by just a small value. It just means that Bifrost recognizes this as a more solid object, and therefore it will mean your collisions will have that bit better accuracy and quality to them. So it's a good idea to always make sure that your colliders are kind of more solid rather than just using flat planes. Now, we can lower the master voxel size to fix this, but we can actually improve the floor to begin with to see if that works, because, you know, it's only a flat plane. So we can give some thickness to the floor, and then if that still doesn't work, it might improve it a little bit, but still not enough for the absolute final quality. But of course, every time you lower the master voxel size, you're then adding more particles, and then of course you're going to be affecting the performance. So this is the balancing act that you're constantly going to have to juggle between when working with Bifrost. And it could be that for this moment in time and for this particular effect, it doesn't really matter about that, because, you know, we want to just get the rough general behavior of our liquid in place and working, and then we can do the refinement later on further along the line in our pipeline. So now we come to what I consider to be one of the most important and fundamental aspects to Bifrost, and something that you should be aware of when starting to do any simulation work in Bifrost, and that's working units. Specifically Bifrost's working units and the relation to your linear working units in Maya. These are the units that you would set in your Maya preferences. If you recall earlier in the video, I mentioned that as soon as you start to work with Bifrost Fluids, real-world physical properties are applied, and that also applies to the values within these properties here in the attribute editor. So what does that mean, and how does this apply to our scene and simulation? And this is where things can get a little complex, so I will try my best to keep this as simple as I can without getting too deep. So Bifrost is based on real-world units to physical and measurable properties like velocity, density, and gravity. And what that means is when we see a value here, say under the gravity magnitude, this is an actual real-world value. It's not random or made up. And this value corresponds to 9.8 meters per second squared. And it corresponds to the acceleration, the actual acceleration of an object falling due to the Earth's gravity. Now, the value of 9.8 meters per second squared means that when an object falls to the ground due to gravity, for every second of time that passes, the rate, as in the speed that the object falls, increases by 9.8 meters per second. Now, our timeline is 120 frames long. That corresponds to being 5 seconds, because our frame rate is 24 frames per second. So here at frame 24, we're 1 second into our timeline. And when we get to the next second at frame 48, our fluid's velocity should have increased by 9.8 meters per second. And this will continue for every second or every 24 frames going forward from this point. Now, Galileo discovered that this rate of 9.8 meters per second squared is consistent regardless of the objects that are falling. And Newton and his second law of motion describes the simple relationship between the acceleration of an object that's falling and its mass and the net force, as in its gravity, that's acting on that object. And essentially, the gravitational force is proportional to the mass or weight of the object. Or, in other words, for two objects of different weights to fall at the same rate, the force, as in the gravity affecting them, will be different. As an example, a 1 kilogram object experiences a gravitational pull towards the Earth of 9.8 newtons and accelerates at 9.8 meters per second squared when it falls. But an object of 100 kilograms experiences a force of 980 newtons so that it can fall at the same rate as the 1 kilogram object. So I think I have that generally correct. My physics is somewhat rusty, so I'm happy to be corrected. So what does this all mean, and how does this relate to Bifrost? Well, this becomes relevant in relation to Maya's working scene units compared to Bifrost's units, and the size of your environment and the objects contained within it. It's important, perhaps essential, to understand that Bifrost's working units are independent of the working units of your scene. Bifrost doesn't consider the linear setting in Maya's preferences at all. Bifrost is based on real-world units, and it defaults to the assumption that when Maya's linear units are set to its defaults of centimeters like mine are, then one visible grid unit is equal to 1 meter. So if we apply this to our scene and our grid, my grid is set to 100 units square. So that means Bifrost is assuming this to be 100 meters square. And I've got my grid lines set to every 10 units. But if I set them to every 1 unit, Bifrost would see this as for every centimeter here, it sees it as 1 meter. So then if we look at the emitter object itself, when I created it, I set the radius to be 20 centimeters, meaning a diameter of 40 centimeters. But Bifrost will interpret this as meters, so it's applying a 9.8 gravity force to an object that it thinks is 40 meters wide. And that's really some size, because 40 meters is just 10 meters short of the length of an Olympic size swimming pool. So imagine this sphere being as big as that, with fluids being emitted from it. Same as the floor, which I scaled up to just under 180 centimeters or units here under in my channel box. Bifrost will see this as just under 180 meters, which again is huge in real world terms. Same for the height above the actual ground that I placed my sphere emitter object. I wasn't very precise, so I used the measuring tool in Maya and it came to approximately 60 centimeters, which isn't too much off the ground. But of course, in Bifrost's world, it thinks it's 60 meters, which is actually really quite high. And that's actually higher than what you see competitors dive at the Olympics. So essentially what this means is that our objects may look okay here in the scene, but they're not really in the correct scale relative to each other, and also probably not proportional to Bifrost's working units either. So they're far from ideal for the values in Bifrost properties to be applied correctly. Essentially, in Bifrost's world, these objects are huge and gigantic. Also, another value to consider is in the emitter properties of our liquid. And if we just take a look at those here, under the physical attributes, there's a density setting. Now the default value is 1,000 units, which is approximately the density of water in kilograms per meters squared. Now our scene is in centimeters, so that means that the density of water should really be only about 1 gram per cubic centimeter. But Bifrost, of course, is interpreting our object as meters, which basically means we're emitting a huge amount of water from a really big object in a really big environment. So what do we do here to compensate? Because this is perhaps why our simulation is moving so slow. Everything's so big and dense. Now you might assume that changing Maya's working units would resolve this, because we could go into our settings and preferences here and change the working units from centimeters to meters. But according to the documentation, that won't work, because it states that if you change Maya's linear working unit to meters, then it considers a grid unit to be 100 meters. So if we go back to our grid again, and if I set my values back to that, so a grid unit here is every 1 unit. So at the moment, Bifrost would consider this single grid unit here to be a meter. But if I change the working units to meters, it then thinks that each one of these is actually 100 meters. And if I change this working units to say millimeters, it then assumes that the grid unit is actually 0.1 meters. So that's not really going to work. Instead, what we need to do is adjust the properties in Bifrost itself to compensate, especially when the scene and objects haven't been created in relative scale of, say, 1 centimeter to 1 meter. My scene is set to a scale of 1 centimeter equals 1 centimeter. So we need to change the gravity magnitude, and we also need to change the density of our fluid or water. So we change the gravity magnitude from 9.8 to 980. That's 9.8 times by 100, because 100 centimeters make up 1 meter. Essentially what we're doing is we're converting the value from 9.8 meters per second squared to 980 centimeters per second squared. Then we need to go into the emitter properties and change the density. So we need to change the density from 1,000 units to 0.001. So this is basically 1,000 kilograms per meter squared to 0.001 kilograms per centimeter squared. So essentially all we're doing is we're converting the values from meters squared to centimeters squared. So now we have to see what difference this actually makes. Now I've changed some of the values here, but I haven't actually done the caching yet because this is probably going to really affect now the speed and performance of my scratch caching. So what I'm going to do now is I'm going to skip ahead to save you guys watching me do this, and then we'll take a look at the results. So after some testing and caching, here's the result. And the caching took a long time, easily around 45 minutes. And I had to increase the master voxel size to 2 so that I could get some reasonable performance from the actual caching. So rather than trying to play this out in the viewport, because it really does affect the performance, I can scrub it here and already you can see the difference in the simulation straight away. But you don't really see this until you compare it against the original version that we actually had. So this is what I've done here. So on the left, I've got the original render I'd done, and on the right is we've got the new one. And when we play these back side by side to the same length, we can really see the difference. So on the new one, we can see that already we've got the fluids are really flowing a lot faster, and the behavior and the look of it looks a lot more believable and certainly more credible. Whereas on the left, if we look here, when we get to frame 24, which is our first second in time, our fluids here on the left have barely started to fall, and they're going to take some time to even catch up. So what this shows is that when wanting to use Bifrost, you really have to think about scale, both how your scene's environment and objects relate to each other, and how they relate to how Bifrost works. And this is so important because if you don't take this into consideration, then you can spend a lot of time adjusting the values here in the properties and going around in circles without realizing the real issue. And I'm sure that this could be where many have perhaps struggled in the past in trying to get anything realistic out of Bifrost. So in terms of the best approach, well, this will depend on how you have things set up. There's nothing wrong in keeping your Maya units to centimeters, but then you have to adjust your object scale and Bifrost values to compensate. So you have to make sure that the objects are in relative scale to each other. An alternative could be that you could keep the scale at 1 centimeter to 1 meter, but model very large and small objects to compensate so that you can actually keep the default values in Bifrost as they are. You don't have to change any of these. So again, how you work is entirely down to you. Okay, so if we take a look at our scene and simulation now, it's not too bad, it's looking a lot better, but there's still plenty wrong with it. At least now we have a better understanding of how Bifrost works, and we can take that into an entirely new scene if we wanted to. There's one last thing to cover though in understanding some of the basic principles. And this has become very relevant now in this scene, now that we have our simulation moving faster and spreading into the actual scene. Now, when I first started to cast this scene out after making those adjustments, it was taking a very long time. And this was because the simulation needed more calculations. You know, we changed the density and the gravity, which meant our particles were moving faster. They were colliding with our ground object. And also the particles are spreading further into our scene. And even though we have particles going outside the camera view like we have here, those particles are still visible to the scene, and so therefore they're still being calculated. So this is where the concept of culling and adding kill planes and kill volumes can help, because by adding these to your simulation and scene, they really allow you greater control and allow you to literally kill off any particles you don't need without actually jeopardizing the quality of the simulation. So this is what we're going to do now. Now, looking at my scene, how far my particles go out, it could really do with some culling so that we're not wasting computation time with all these particles down here, which are falling way below the ground. So the first thing I'm going to look at is adding a kill plane. And this is perhaps the simplest way of culling your particles in your scene. So with my simulation selected, we need to go to the Bifrost Fluids menu, and from the Add section, choose this option here, Add Kill Plane. Now that will add the kill plane object to my scene, and my simulation will start caching out. Now it's a little bit small because the object is actually here at world center. So I'm just going to scale this up so we can see it a lot more in the scene, and then I'm going to start caching my simulation out. But with this kill plane in place, what I can do now is if I just scrub my timeline forward, look what happens when my particles hit that kill plane. Whenever they come into contact with the kill plane, they're just essentially culled. And once culled, they won't be computed as part of the simulation. Now, we can translate and rotate this plane into position to suit our needs, but the plane is infinite, so there's no need to scale it in terms to make it fit anything. You just probably want to scale it in terms of visibility, and you can even add multiple kill planes if needed. So you can see here that if you look at the side, as soon as my particles kind of hit the ground here and then fall off the side, because my kill plane's at ground zero, they're immediately culled. Nothing is going below ground zero. Now, for example, we may want to alter this and say, well, could we lower the kill plane and just allow for a little bit more simulation to go off the edge? And that's very easily done. You just essentially select it and move it. And as soon as you move it, of course, your simulation will need to recalculate. And of course, that'll start to recache. And we can see the timeline starting to fill up. And now when we just scrub to a certain point, you'll see more particles going off the edge. And of course, when they fall down due to gravity, as soon as they hit the kill plane, they'll be culled and they won't go beyond it. So we have some good culling going on, but I don't really like it because I want to have a little bit more control. The kill planes can be just really like a blunt instrument because they're infinite. So although you can rotate them and translate them, they don't really give you too much control. They're often a good thing to have on the ground. So if you've got objects above the ground that have simulations, you can often put this kill plane on the ground below any objects or ground planes to absolutely make sure that if you've got any gaps appearing and the simulation goes through those gaps, then as soon as they hit ground zero, then they're going to be culled anyway. So to give more control, we now want to consider using a kill field instead. So kill fields can be used to delete unwanted liquid foam and even aero particles in a Bifrost simulation based on various criteria. And you can limit the effect to a specific volume using a closed polygon mesh in the scene or using an implicit shape. So with our simulation selected, we'll go to the Bifrost menu. And again, under the Add section, you want to look for the option that says Kill Field. And we're just going to add it there. So what this basically does is it adds a very small object into our scene, basically a small cube, which we can't really see at the moment. If I was to just scale this up, now this is essentially our bounding box or our field that we're going to use to kind of kill off or control or cull any particles. Now watch what happens when I start to intersect with the actual emitting object with this shape. And you can begin to see that we're culling the particles from within the volume. So anything inside this volume is going to be culled. Now, in the attribute editor, there's a few things that we can use to control this kill field. And you have a lot more control here than you do with a kill plane. Now, for starters, you can determine how you want to cull your particles. So at the moment, we're just using this bounding box, this shape. And we can even control the shape of this as well with these presets like sphere or cylinder. And we can even control the fall off as well. If you look, when I just drag the slider there, you can begin to see a little bit of a fall off occurring based on whatever value I put in here. Now, of course, if I scale this up like so, we're going to cull everything inside the volume, but it's kind of not what we want. We want to basically, we want to have the simulation occurring inside the volume and cull anything that's going to go outside it. So this is where the invert function comes in. So clicking this will basically mean that this cube acts as a bounding box. So the simulation will be confined to this particular shape. And of course, we can scale it as well proportionally to make it fit. So these kill fields are very good at, if you want to, maybe you can shape them to different objects. So if you've got buildings in a scene, for example, you can add multiple kill fields and place them in your scene and just give them almost like a bounding box, so that you know that any particles or simulation that's going to hit it are not going to protrude or be calculated and you can't see them. So now if I just let the caching go to work a little bit more, then we can see basically how this is working, and we can see we've got our simulation working as normal, and then I can just maybe rein it in a little bit and just to kind of see the culling in full effect. So when we scrub the timeline now, we can see that as soon as it hits the boundaries of the volume, it's completely culled. Now we do have a few particles perhaps going underneath here. You can actually add a kill plane to this as well. So you can use the kill field and a kill plane in conjunction with each other, just to that extra layer of culling, because there's always going to be some particles that perhaps maybe bounce through. And you can see here, for example, we've got some that seem to fall through the actual ground, but that's mainly down to the resolution of the master voxel size. So you can begin to see how all these values and parameters and things that we're using to control the simulation are kind of all interrelated. There's some additional controls here as well, because we can even choose to cull the properties by not only the boundary but also a lifespan, and we can give the particles like a certain age, so that when they get to a certain point, you can see I've just changed it there and they've all disappeared. And of course it will now start to cache out, but of course how you set these will be very much determined on your objects and the scale of your scene. But it's good to have another layer of control, so that not only are you confining the particles to an actual border and boundary, but then you can also choose to still cull those particles within that boundary by using, say, an age range. So we're now reaching the end of this video tutorial. We've got the basics all established and the fluid simulation working. There's just one small thing to highlight now, and maybe something that you might not have realized, and that's that you can actually render the simulation right now. If I was to quickly add an Arnold light into my scene and change the renderer over, when I render, we can actually see the liquid being rendered. What this is the Bifrost mesh, and this is the node here in the outliner, which you may not have noticed was created as soon as we added liquids into our scene. Now previously, when working with fluids, you would need to create the simulation first, then get that to a final quality, then do a final cache out of that simulation, and then use that cache to generate a mesh, and then you could render your fluids. Now Bifrost does this automatically now, so as soon as you add any of the nodes in your scene, the Bifrost liquid mesh is automatically created. But what you get, I guess, is kind of a bit like a preview mesh, and it isn't necessarily representative of the final output, but the quality is just to see how the liquid might look. And it even assigns a standard Arnold surface shader to it, and of course you can then choose any one of the presets that are available here. But even on this simple render, you can begin to see what's working and maybe what isn't working. Now the default mesh is hidden from view, even though it's in the outliner. And if you want to see it, then you need to go to the liquid shape node. You go to the liquid shape node here, and in the attribute editor, scroll down until you come to this heading here, Bifrost meshing. Open it up and you'll see that there's a box that says enabled. So you just need to basically turn that on. And then as soon as you turn that on, you'll see the mesh in the scene. And when you select it, you can see the tessellation. It will look somewhat blobby, to be honest, because like everything else, the quality is dependent on the simulation. So really, this is why you should focus on getting the simulation and the behavior working correctly first with just enough particles, and then start to tune it up by increasing the resolution of your simulation of voxels using the master voxel size. Because once you've then got that higher resolution, then this mesh quality will then begin to increase as well. So remember, our voxel size is quite high at the moment, which is why the mesh looks a little bit blobby. But again, if we were to lower that value, increase the number of particles, increase the number of voxels in our scene, then that would have an immediate impact on the quality of our mesh and would start to get a far better, higher quality output. So although this is useful to have, it's important not to fall into the trap of doing renders all the time here. I would just use this render as just a way of doing a quick preview, just to maybe sanity check what you've done so far and just make sure things are working. My scene is not the most complex in the world, but if you've got a more complex environment and emitter objects, then you may want to do a render from time to time just to check some things out. And at least then you can make maybe some basic creative decisions about going in a particular direction. But the main important thing is that you can do the render, but also focus on getting the simulation correct first. Get the behavior working, get all your settings working in Bifrost, and then tune it up using the master voxel size. So this has been a very basic introduction and orientation of Bifrost Fluids for Maya. I've covered some basics like creating emissions, colliders, and how to understand the core principles of Bifrost's real-world values. In the next video, we're going to take what we've learned from these basic principles and apply them to a more believable scene, and then look to build it up to a more realistic and final quality simulation and hopefully final render. Thanks for watching, and I'll see you in the next video.